Hello. Today we're going to talk more about lines and planes. In the previous video, we talked about how to form an equation of a line as a vector value function, and the equation of a plane and the properties that it has. Today we're going to focus on how to apply both of these properties into questions that may be more complex. As a rule of thumb, if you would like to try these problems before the solution is shown, please feel free to pause the video and do so. We're going to start with the line of intersection between two planes. This question says find the line of intersection that passes through the planes 2x minus 3y plus z equals 5 and negative x plus 4y plus z equals 0. So here I have drawn two planes, and we want to find this line that is created by the intersection of these two planes right here. Now the strategy that we're going to impose is we're going to find the normal vector of both planes first. And remember that the normal vector is perpendicular to the plane and points outwards from it. Now if you take a look here, the normal vectors seem to intersect. And if we find the cross product between the normal vectors, we seem to get a line that should be parallel to the line of intersection. So let me just draw this a little bit better. So the reason this works is because the cross product between two vectors forms a third vector that is perpendicular to both two vectors that are in the cross product equation. So this parallel vector to the line of intersection is perpendicular to the normal vector of both planes. So let's try doing this. First, I'll form a vector A, and this vector will be the normal vector of the first plane. So this is plane A, and this is plane B. How do we find the normal vector from a plane? Well, we take the coefficients of each variable x, y, and z, and that forms us into a vector we can use. So this vector would be 2, negative 3, and 1. And this vector is perpendicular to the plane 2x minus 3y plus z equals 5. Now we'll form another vector, this time vector b. And this vector, we want it perpendicular to the second plane. And we do the same thing. We take the coefficients from each variable, so negative 1, 4, and 1 here, and we put them into a vector. Now, these two vectors are both normal vectors, and normal vectors are perpendicular to the corresponding plane. Now, the next step will be to take the cross product between these two vectors. So, A cross B. And taking the cross product between these two vectors will give us a third vector that is perpendicular to both vector A and vector B. So I'm going to create my 3 by 3 matrix and take the determinant of it. The first row will be our basis vectors I, J, K. The second row will be the components of vector A, so 2, negative 3, 1. And the third row will be the components of vector B, so negative 1, 4, 1. Now, we want to expand along the first row. This will give us I times the matrix negative 3, 1, 4, 1 minus J times 2, 1, negative 1, 1 and K times 2, negative 3, negative 1, 4. If you want a more detailed explanation on how this is done, please check out my cross products video. Now, finding the determinant of each of these matrices, we get negative 3 minus 4 equals negative 7. We get 2 minus, and we have a negative 1 here, so it's plus 1 equals 3. And 2 times 4 is 8, so 8 minus a negative 3 times negative 1 is 3, so 8 minus 3 equals 5. We get negative 7i minus 3j plus 5k, because we don't forget about the negative here. And if we put this into a vector, we get negative 7, negative 3, and 5. Now this vector represents the direction vector that is parallel to this line of intersection here. From a previous video, we stated that in order to form an equation of a line, and the equation of a line is right here, t times v, we need the point, and in this case the point doesn't really matter where it is since we want to find the entire line, and then we need a direction vector. So we found the direction vector already. That's -7, -3, 5. And we know that the vector has that direction, so it's pointing in that direction. We need the point now in order to place it in the right spot. We need to move it to where this line is. In order to find the point, we need to find a singular point that both of these planes have. And the way to do that is to use a system of equations. So a system of equations where 2x minus 3y plus z equals 5 and -x plus 4y plus z equals 0 would give us a value in which both the top equation and the bottom equation would have the same point, because we want to find one point. The easiest way to do this is we're going to set z equal to 0. So we want to eliminate a variable from the equation. By setting this equal to 0, we can solve for x and y, because a system of equations with two equations can solve for two unknowns. And when we solve for two unknowns, we can find out what a point is. So let's simplify this by getting rid of the z component. We get 2x minus 3y equals 5, and -x plus 4y equals 0. To solve the system of equations, it's easier to use elimination. So to eliminate, we want to multiply the bottom equation by 2. Multiplying the bottom equation by 2, we get 2x minus 3y equals 5, and -2x plus 8y equals 0, because 0 times 2 is still 0. So apply equation 2 by 2. Now we can add both equations together in this step, where we get 0 plus 5y is equal to 5. Now we can solve for y, because we basically eliminated the variable x. And from this equation, we can see that y is equal to 1. Now let's find out what x is. To find out what x is, we plug y equals 1 into one of these equations. Let's just use the top one. So 2x minus 3, and now we know y is 1, so we can plug that in. So that equals 5. We have 2x minus 3 equals 5. 2x equals 5 plus 3 is 8, so x is equal to 4. Now as we know z is 0, because we set that equal to 0 at the beginning. So our point is 4, 1, 0. Now that we have our direction vector and we have our point, we can construct a line of intersection. Now, I'll put it up here. So our line is 4, 1, 0, which is our initial point, plus t times -7, -3, 5. And simplifying this, we get one vector, so 4 minus 7t, 1 minus 3t, and 5t. And this is the equation of the line of intersection that passes through the planes 2x minus 3y plus z equals 5, and -x plus 4y plus z equals 0. Now let's talk about how to find the angle between two planes this time. So we have the same figure as from the first graph, and this is not to scale, it is just a representation of what we're trying to find. So what we want to try to find is this angle between the two planes. Now we can use the same strategy as before. We want to use the normal vectors to our advantage. So what can we do with the normal vectors this time? So as a reminder, the normal vector should be perpendicular to the plane, like so. So this angle between the two planes is the same as the angle between these two vectors. And we've talked about how to find the angle between two vectors in one of the prior videos. If we have two vectors, the angle between two vectors is equal well, let me just write this first. So we have the angle is equal to our cosine of u dot v over the magnitude of u times the magnitude of v. Now we can use this to find the angle between the planes, but there's a catch. This time we want to add absolute value signs to the dot product, because remember we talked about how if the dot product is greater than 0, then it will make it so that the angle is acute. So if the dot product is greater than 0, it means that the angle is acute, or less than 90 degrees. And if the dot product, so the dot product is greater than 0, then the angle is acute, or less than 90 degrees. If the dot product is less than 0, that means it should be negative, then the angle between the two vectors is actually obtuse, or greater than 90 degrees. So when we're finding the acute angle between the two planes, we want to make sure the dot product is positive, so that we don't accidentally find this angle right here. So let's try to find that. First, we need to find the normal vectors between the two planes. The normal vectors, again, are just the coefficients between the planes. So we have the first plane, 3, 4, negative 2, which will be vector A. And the second vector, vector B, represents the second normal vector, and we can find it from the second plane. So we have 1, negative 2, and 3, which are the coefficients of the three variables. Like so. Now all we do is we find the dot product and the magnitude of both vectors, and then we plug them into the equation and solve. So let's first solve for the dot product between A and B. And the dot product is pretty simple. We just find the product of each component. We multiply each component together, so 3 times 1, and we add all of them together, so plus 4 times negative 2 plus negative 2 times 3. Simplifying this, we get 3 minus 8 minus 6. 3 minus 8 is negative 5, minus 6 is negative 11. The dot product between A and B is negative 11. Now, negative 11 is a negative number, which means that the angle between the normal vectors is obtuse. However, we don't want to find an obtuse angle between the two planes. We want to find the acute angle. So that is why the absolute value signs on the equation are really important, as they will give us the acute angle and not the obtuse angle. Now we will find the magnitude between vector A and vector B. The magnitude is we want to take the square root of each component added together. So 3 squared plus 4 squared plus 2 squared. And yes, I know that this is negative 2, but since we're squaring each component, the negative numbers do not matter as much. So 3 squared is 9, plus 4 squared is 16, plus 4 is 4. So we have the square root of 29. Now we can find the magnitude of vector B. And that is equal to the square root of 1 squared plus 2 squared plus 3 squared. 1 squared is 1, plus 2 squared is 4, plus 3 squared is 9. So 1 plus 4 is 5, plus 9 is 14. So that's just equal to the square root of 14. Now let's plug this into the angle equation. The angle between the two planes is equal to cosine to the power of -1, or inverse cosine, or r cosine, times the absolute value of the dot product, so I'll just put 11 here, over the magnitudes multiplied together, so square root of 29 times the square root of 14. Now if you plug this into your calculator, and make sure that the calculator is in degrees if you want degrees, or radians if you want radians, you get 56.9 degrees. And that is the acute angle between the two planes, 3x plus 4y minus 2z equals 0, and x minus 2y plus 3z equals 9. As a side note, notice that we didn't use the number onto the right in this question, because that just represents the value that the plane is shifted away from the origin, and we're not concerned about that. We're concerned about the angle between the two planes, and that's why we solved for this number right here. Next up, we're going to talk about parallel, perpendicular, or neither lines and planes. So in the first video, we talked about parallel, perpendicular vectors. We know that vectors are parallel when they're scalar multiples of each other. And we know that vectors are perpendicular when they are orthogonal to each other, and the dot product is equal to 0. So this will apply to lines as well, because lines are made out of two things. We have, to make a line, we need two things, right? We need a point on the line itself, and we need a direction vector. So we're considering the direction vector here because that tells the line where to point. And if this direction vector upholds to the rules of parallel, perpendicular, or neither lines, we know that the lines are either parallel, perpendicular, or neither. So if we find the direction vector from each line, we can know if they are parallel, perpendicular, or skew. So the third option for this is skew, or intersecting. And we'll talk about this. So lines are intersecting when they touch each other in the same spot. So let's say these two lines may intersect at the same spot, but the angle between the two lines may not necessarily be perpendicular. And skew lines are lines that do not intersect at all and are not parallel. So in the 3D space, we can have lines that are pointing in different directions, and they'll never touch each other, but they point in different directions, and that's why we call them skew. So skew lines never intersect and are not parallel. And intersecting lines, they do intersect, but not at 90 degrees. So when we're saying, if we say that the lines are neither, this is what we mean. They're either skew or intersecting. So let's find the direction vector from both lines. For the first line, we have r of t, and we can write r of t here. This is equal to 2 plus t, negative 4t, and 1 minus 2t. Let's break this down. So this is equal to the point, and for the point we just look at the numbers before it. So we have 2, 0, 1, plus t times the direction vector. In the direction vector, we find the coefficients before each t number. So the coefficients give us 1, negative 4, negative 2. Remember the line equation is r naught plus t times the direction vector v, which means that this must be the point and this must be the direction vector. and we are concerned about the direction vector, so I'm going to underline this and analyze the next equation. So the next line, r of s, is 3 plus 3s, 1 minus 12s, and 3 minus 6s. Breaking this down, we get the point equal to 3, 1, 3, plus t times the direction vector. The direction vector is composed of the components, or the coefficients, multiplied to each parameter s. So we have 3, negative 12, and negative 6. So we have our point here, 3, 1, 3, and we have our direction vector, 3, negative 12, negative 6. So now that we've found both the direction vectors from each of these lines right here, we can analyze it and say if this is parallel or perpendicular. So lines are parallel when they are scalar multiples of each other. So let's test for that. So scalar multiples means that if we do 1, negative 4, negative 2, then this will be equal to a scalar c multiplied by the second direction vector, 3, negative 12, negative 6. So is there a scalar that would make this vector equal to this vector? There is, and that scalar is 3. So if c is equal to 3, or actually 1/3, if c is equal to 1/3, we have 3, negative 12, negative 6. We can distribute the scalar to each of the components, and we get 1, negative 4, and negative 2. And so since this vector is the same as the original vector, or the vector direction vector from r of t, we know that these two lines are parallel. And we know this because their direction vectors are scalar multiples of each other. So our scalar here would be 1/3, and that would make both lines equal, both directions vectors equal to each other. Now, what if this was between planes? So determine whether the planes 2, negative 3, 2x minus 3y plus z equals 12, and 3x plus 2y equals 1 are parallel, perpendicular, or neither. For planes, we want to take a look at their normal vectors. Their normal vectors will tell us if the planes are parallel, perpendicular, or not. Now, planes cannot be skew like lines, because planes are in the third dimension. Lines are in the second dimension. They only have 2 dimensions, right? So they can be skew because they can be in the 3 space without ever touching each other and not being parallel. But planes cannot because they exist in the third dimension. So looking at the plane's normal vectors, if the normal vectors are scalar multiples of each other, then they're parallel. If we take the dot product of the normal vectors and it equals 0, then it is perpendicular. If none of these are true, then we can say it's neither. So let's first take the normal vectors from each of the planes. The first plane, normal vector, I'm going to say it's A. And to find the normal vector, we just take a look at each of the coefficients. So 2, negative 3, 1. And that is the normal vector for the first plane. And remember, the normal vector is perpendicular to the plane itself. Now B, which is the second normal vector for the second plane, is 3, 2, and since there's no z component, the z component is 0. So we have 3, 2, 0. Now, let's check if they are parallel to each other. So if the normal vectors are parallel to each other, then the planes are parallel to each other as well. We check for parallel by saying, is there a number, or is there a scalar c, in which multiplied to the second term will give us the first vector? So is there any value for c in which makes these vectors equal to each other? And the answer to that is no. It's really easy to tell because, well, you have c times 0, and any number times 0 is always going to be 0. And in this vector, we have 1 right here. So since c times 0 equals 1 will never happen, right? C times 0 equals 1 is false. We definitively know that these two vectors are not scalar multiples of each other. Now let's check for perpendicularity. Now we know that two vectors are perpendicular if the dot product between them is equal to 0. And we also call this orthogonality. So if the two vectors dot product are equal to 0, then two vectors are orthogonal. So let's find the dot product between vectors a and b. The dot product between vector a and b is 2 times 3 plus negative 3 times 2 plus 1 times 0. Simplifying this, we get 6 minus 6 plus 0 equals 0. Since we get 0 as the answer between the dot product between a and b, then the two planes are perpendicular. So this tells us that vectors a and b are perpendicular to each other. And since the vectors a and b are normal vectors to the planes itself are perpendicular as well. Orthogonal. So the planes are perpendicular to each other because their normal vectors are orthogonal. Now moving on, here we have a question in which we want to find out whether a line and a plane are parallel, perpendicular, or neither. Now this is a little bit tricky because this is between a line and a plane. Now we know that the plane, we have to deal with the normal vector, and the normal vector is perpendicular to the plane itself. So if we're comparing the normal vector to the line, we have a few cases. And line. So if the normal vector and the line are parallel to each other, then what will happen? Remember, we have a plane and the normal vector is perpendicular to the plane itself. If this normal vector is parallel to a line, so parallel, then the line and the plane have to be perpendicular. So line and plane are perpendicular in this case. If the normal vector and the line are perpendicular to each other, so like if this is not the case now, but we have the line perpendicular to the normal vector, this, then what happens is the line and the plane will now be parallel to each other. So this is kind of like backwards logic, in a sense. So let's find the direction vector of the line and the normal vector of the plane, and then analyze it further from there. So the line is given by r of t equals 1, 2t, or 1 plus 2t, negative 3t, negative 4 plus t. And breaking this down, we can break this down into a point, and the point is 1, 0, negative 4, plus t times the direction vector 2, negative 3, 1. So the point comes from these constants before every term, so 1, 0, negative 4. And the direction vector comes from the coefficients multiplied to each variable, so 2, negative 3, and 1. And we are interested in this direction vector. Now let's find the normal vector, and for normal vector I'll call it vector A. Looking at this plane, the normal vector is composed of the components of each coefficient of each variable. So 1, 1, 1. And that is the normal vector to the plane. Now let's test if these vectors are parallel, perpendicular, or neither to each other. Parallel. We know it's parallel when they're scalar multiples of each other. So is there a scalar that would make this equation true? So 2, negative 3, 1 is equal to c times 1, 1, 1. And the answer to that is no. This is false. Because 1, 1, 1 and 2, negative 3, 1 can't be equal to each other when multiplied by a singular scalar, because a scalar is distributed across all three components. And 1 and 2 have a difference multiplier of 2, and 1 and negative 3 have a different multiplier of negative 3. So since those two ratios are different, these vectors cannot be parallel. Now let's check if they're perpendicular. Now we know that two vectors are perpendicular when the dot product is equal to 0. So let's find the dot product between these two vectors. So we have 2 times 1 plus negative 3 times 1 plus 1 times 1. And simplifying this, we get 2 minus 3 plus 1. 2 minus 3 is negative 1. Negative 1 plus 1 is 0. So these two vectors are perpendicular to each other. So is the answer just perpendicular? Well, no, because we want to find the relationship between the line and the plane. Remember that we take this vector from the normal vector of the plane, which means that this vector itself is perpendicular to the plane. Now, if this vector is perpendicular to the plane as such, and the line is perpendicular to this vector, then we know that the line and the plane have to be parallel to each other. So the answer to this question is that the line and the plane are parallel to each other because the direction vector and the normal vector to the plane are perpendicular to each other. The last topic we're going to talk about for today is how to find the distance between a point and a plane. So first I'm going to start by drawing a picture in which I have a plane right here and a point. And we want to find the perpendicular distance from the point to the plane itself, like this. So to do this, we can first draw a reference point on the plane in which we will use to look at. So calling the point S and calling the reference point on the plane P, if we draw a line between point P and S, then we can clearly see that this is a right triangle. So using this right triangle, we can start to find the value of D. The angle between the line P and S and the leg that's created by S to the plane, we can call that theta. And we can find out what the value of D is by using trigonometry. So which trigonometric function has to deal with adjacent legs, because that's what we're trying to find. And that would be cosine. So cosine of theta would equal d over this hypotenuse right here. So the hypotenuse is given by the magnitude of the vector formed by PS. And that's how we find d, because we can then isolate it, getting us the magnitude of PS times cosine theta. Now there is an issue here. We don't know what theta is. The question doesn't give us theta. It gives us a point, and it just gives us the equation of a plane. So what do we do now? Well, we can make some substitutions. Keep in mind that we have u dot v equals the magnitude of u times the magnitude of v times cosine theta. So what if we made the substitution here? In order to make the substitution, we need the magnitude of another magnitude of the other vector pointing at it. So this vector that points in the same direction as the line D is actually the normal vector to the plane. So we will use that to our advantage. If we multiply both sides of this equation by the magnitude of the normal vector n, then we get the distance times the normal vector n is equal to the magnitude of PS times the magnitude of n times cosine theta. And this is equal to the dot product between the vector PS and the normal vector n, like so. Now if we isolate d again, we just divide this to the other side, we get d is equal to PS dot n, they're both vectors, divided by the magnitude of the normal vector n. And the last step is just to put absolute value signs around it, because the distance cannot be negative. So the distance must always be positive, and that's why we have the absolute value signs around it. Now, since we have this formula, we can solve for the distance now. First, we got to create a reference point. And the easiest way to create a reference point is just to see if 0, 0 works in the plane. So if we rewrite this such that all the variables on the left side, so negative x plus 4y plus z equals 0, and the constant is on the right side, we can see that the point 0, 0, 0 lies on the plane. So using this, we can say that p is equal to 0, 0, 0. Now, the point S is 1, 0, negative 1. So PS, and this is a position vector now, so we take the final point minus the initial point. We have 1 minus 0 is 1, 0 minus 0 is 0, and negative 1 minus 0 is negative 1. So now we have our vector PS. Now, let's find our normal vector. And our normal vector is pretty easy. We just find the coefficients of each term in the plane equation. So we have negative 1, 4, and 1. Like this. Now the third thing we need is the magnitude of vector n. So let's find that. We take the square root of 1 squared plus 4 squared plus 1 squared. And doing this and simplifying, we get 1 squared is 1, 4 squared is 16, so 1 plus 16 is 17, plus 1 squared is 1, so the square root of 18. Now we plug this into the equation, and doing this, we get the distance is equal to the dot product between p and n, and we can find that by just doing 1 times negative 1 plus 0 times 4 plus negative 1 times 1 over the magnitude of n, which is the square root of 18, and we're going to take the absolute value of this. Negative 1 times negative 1 is negative 1, 0 times 4 is 0, negative 1 times 1 is negative 1, negative 1 minus 1 is negative 2, and because of the absolute value, that just equates to 2. So the answer to this is 2 over the square root of 18. And if you want to get a decimal answer by plugging it into your calculator, the decimal answer turns out to be 0.471 units, which is the distance from point S to the plane.